this is very important to human survival, like study of water, study of hydrodynamics, study of how things have to move from one place to another. Because throughout history, wherever there was water, there was life. So everything is around water somehow. You can drink it, you have to have it to survive, and you also need it for your factories and stuff. Now, right now, a lot of hydroelectricity is produced in the world from constructing dams, right? Okay, so since this is very important, let's talk about the fact that people have been trying to study this for centuries. And physicists, when they came along, of course, we wanted to join in the fun. And what do? We always construct equations. So let's talk about the different ways that people try to study fluid dynamics. So initially, there were people who were trying to study the formalism of how water flows and stuff, and they were trying to study them. There were two trains of thought. One was, okay, we still have to study it, so we'll go back to our Newtonian mechanics. In our Newtonian mechanics, what did we do? We called something a particle, and then we studied that particle's motion. We calculated its v, we calculated its acceleration, its velocity, its speed, its position over time, right? But that was one particle. Is fluid one particle?
No.
It is what?
Lots of particles.
Lots and lots of particles. So how do we study lots and lots of particles? So there were two main methods that people tried to come up with. So to describe fluid flow, one, Lagrange, and he came up with a definition that he called fluid particle. He said, I'm going to call my fluid a particle, and I'm going to assume that my fluid is divided into infinitesimally small volume elements. I'm going to call that my particle, and I'm going to study that volume as it moves through space. Got it? So he called that volume a fluid particle. Okay? What does that look like? He said, my fluid particle will look like this. It is going to be a delta V, a small volume element, defined by delta X, delta Y, delta Z. And then he said, as this fluid particle moves through space, I am going to study each one as it moves. It's easy to do it with one, right? Now what happens if you have a billion of them?
I'm going to need some paper.
A lot more paper. A lot more trees will get destroyed. Right? So what can we think of that might actually help us in this case? So, number two, a guy called, he said, think about it this way. So instead of thinking of you sitting on this fluid particle moving down with the flow, he said, what if I just stand at one spot and watch as the fluid flows through? That makes my life easy. Now I'm just standing there watching as the fluid goes through. I can look at it. So if I can figure out the density of the fluid and I can figure out the velocity of the fluid, can I figure out the position from there? Can I also figure out the acceleration from there, right? Remember those graphs we drew, X, Y, Z, and then A, V, T? As long as you give me one of those graphs, can I extrapolate forward or backwards? If you give me accelerations, can I tell you what the velocities and positions would be? If you give me positions, can I tell you what the other two will be, right? So he said, instead of me sitting on the volume element, the fluid particle, what if I just stand in one place and then just watch as things flow by? That's what he did. Okay, so now let's look at the proper definitions of both of these things. Ready? So may I move this a little down so I have room to write things? So Lagrange's idea was divide the fluid into infinite, tiny volume elements called fluid particles and follow each one as it flows. Fine to do it for one, not fine to do it with billions. Then Euler came along and said, don't worry about the history of each fluid particle. Instead, specify the density and the velocity of the fluid at each point in space. So think about it. So you do like, for example, if something is flowing off a pipe, you don't worry about every single particle that's in the pipe. You just worry about a particular cross-section and see how much water is flowing through that cross-section. Got it? So it's like you standing there, like you put a meter right there and see how much flow goes through. So it's like policemen. As the traffic flows through, they don't follow each car. They just stand at one spot and then have their motion detector. They just put the motion detector there and watch as the cars go by. Right? Okay, so that is actually good. However, in this case, what he said was that my density will now be a function of x, y, z, and time. And so will my velocity. So instead of a 3-dimensional coordinate system, we are now living in a 4-dimensional coordinate system, which also includes time. We just went from, oh, we just have an XY coordinate system, but now my volume also has time in it. So when we think of relativity, we usually think, oh, it's a completely different concept. It really isn't. There were other things that helped develop it to that point. Okay, so we're good there? So Euler's method actually is the one we are going to continue forward with, because that seems more reasonable. So every single time when you think of fluid flow, think of you standing there and watching the flow pass. Got it? Okay.